And audio check, I think we're good. Okay, so last time I gave a brief explanation of this idea of torque. Hopefully it wasn't too brief that you have some questions, but brief enough that, well, I don't know where to go from there. But and I also briefly explained this idea of the extended force diagram. There's nothing fancy going on there. It's just a regular force diagram that you draw the actual object, and then you draw where on the object the forces are applied rather than just applying them wherever you want. The reason you need that is because the location of where the force is applied is relevant to the calculation of the torque. And then I just did this brief, keep saying brief, just did this example calculation. This should be a minus there. Right, and by the way, for those who didn't stick around last time, there was a minor correction, and this was with regards to the way I was defining things. There was an issue regarding various signs, so I'll just briefly go over it. There's a negative sign here. Where'd my why is my mouse so skinny? Or my there we go. So here I am assuming that A is positive. So I put a negative sign here because the block is accelerating downwards. So if A is positive, the net force is pointing downwards, so we have to stick a negative sign there. Then this constraint equation holds up, and then everything follows through, because then the equation that we have is T minus mg equals negative ma. And so then we get, so then this equation follows, and then everything else follows through, and nothing goes wrong. And this was the result that we got before, so everything checks out. So we're just going to take a quick detour now that we have torque introduced before we continue on with static equilibrium. So let's talk about rotational work and power. So remember that for translational work, the formula looks something like this. We have the work from A to B is equal to an integral, a line integral from A to B of, not tau, of the force dotted into the infinitesimal path. And the work energy theorem gives us that that's equal to the change in kinetic energy of the object upon which the force is acting, which is, 1/2 mvb squared minus 1/2 mva squared. Now we can do the same thing for rotational work, which is just work done by a torque. So here we have the work done from configuration A to configuration B. This is an integral, again from configuration A to B, of the torque, again as a vector, torque is a vector just like force is, dotted into the angular path that's taken. And that's, again, equal to the change in kinetic energy by the work energy theorem. But this is rotational kinetic energy. I'll put rot here and trans here. So this is 1/2 I omega b squared minus 1/2 I omega a squared. So I just want to be extra clear here. So this is not necessarily a path in space, right? So unlike for translational work, where you would have, an object here and it goes through space with some various force applied and it ends up here, that's not what this d theta represents an infinitesimal element of. Instead, this d theta is the infinitesimal vector obtained via the right-hand rule. So if you have a clockwise, say you curl your hand in the direction of the angular motion, your thumb sticks in the direction of the vector, that indicates rotating by a small angle about some axis. So the point is, for example, maybe you have like a wedge or something like this. Maybe this is your A configuration, and your B configuration maybe looks like this. And so your d theta, well, your path theta ranges from, say, maybe this is, I don't know, 30 degrees. Your theta ranges from 0 to 30 degrees, but the vector. So in this case, d theta, if say that's x, this is y, and then out of the board would be z. So in this case, d theta would be some small angle in the k hat direction, because the rotation is occurring counterclockwise in the xy plane. So we use the right-hand rule. The rotation goes from x. Let me show the. So the right-hand rule is you use your right hand to determine the associated vector of a rotation. So if my hand is in the, there we go. My hand is in the orientation of the paper. Then I start with where the angle is starting, and I end where the angle ends. So maybe that angle. Then my thumb, which points, out, points in the direction of the vector. So that would be the z direction, in the positive z direction. And so that's why we get that it's in the k hat direction. And then the magnitude of this vector is just d theta. RHR is right-hand rule. So the integral here in this very specific case would be something like 0 to, well, what's 30 degrees in radians? 0 to pi over 6. And then it would be whatever the force is, or whatever the torque is, the magnitude of the torque times d theta, assuming that the torque was in the same direction as the path. The arrow is pointing the other way. Would we make k hat negative? Yes, precisely. Yes, you would make k hat negative, because then the right-hand rule would be here, starting off here, curling down to a lower point, and then my thumb would point into the paper. So that would be in the negative z direction. Right. So we can compute rotational work in the same way. It's just a little bit harder to visualize because we're talking about a path through rotation space, like how the angles change rather than how the position changes. But that's the only difference. And then similarly, we can actually ask about how much power a thing does via rotational work. So the way that we compute it is just the same that we would for translational motion. For translational motion, we have power equals dw dt, and that is just f dot v. Yes, yeah, the k hat is just specifying the axis about which the rotation is occurring. Yes. For rotational power, we get that power is still dw dt. It's still the time rate of change of the work, but this time the work is not f dot v. Now the work is not f dot dl. Now it's tau dot omega. So all we did is we swapped force for torque and angular velocity for velocity, just as we normally do. Whenever you have some translational type equation, you can just make it rotational just by making the swapping out all of the variables, all of the translational variables for rotational variables. Right. So this is how you can compute rotational power. So when you start talking about the power output by a vehicle, no, you actually don't need an integral for power in general, because the derivative gets rid of the integral effectively of work. Let's say it's f dot dl. Well, that's just equal to d dot ddt. That is equal to integral of f dot dl dt. And so, more precisely, it'd be the integral of d dt of f dot dl. And basically you get, from the fundamental theorem of calculus, you can, this derivative cancels with the integral. That's the way to see it. Basically, a small chunk of work is f dot dl, and so the rate of change of work is f dot dl dt, which is f dot v. Anyway, right. So let's go back. We're going to be talking about static equilibrium, but I want to first introduce a little bit more, a few more tools used for calculating torque. So let's talk about using geometry to calculate torque. So just as a reminder, the magnitude of the torque is equal to r cross f, the magnitude of r cross f, which is just r, magnitude of r, times the magnitude of f, times sine of theta. Remember that r in this case is the vector that points from the axis of rotation to the location where the force is applied. But a lot of the times, at least in this course, we only deal with torque in a two-dimensional plane, so we don't have to worry about the direction of the torque. More or less, it's often enough just to know whether the torque is positive or negative and what its magnitude is. So sometimes we can use geometry to more easily determine this magnitude, like just using Pythagorean theorem and things like that, to determine something like either the magnitude of r times sine of theta or the magnitude of f times sine of theta. Sometimes these quantities are more obvious than the actual vector themselves. So, for example, let's say that we have a rod, trying to draw a straight rod, with a pivot point here and a distance d here, and maybe we apply a force at the end with some magnitude. This is some angle. Well, the perpendicular bit, we can, how do I want to phrase this? We can compute f sine theta pretty explicitly. F perpendicular is just f sine theta. And that's just the distance between, or that's just this length here. And so you can just explicitly use trig to find f perpendicular, and then multiply that by d, rather than finding the full vector f and then taking the cross product, or similarly finding the magnitude of f. Say you already know f perpendicular. This one doesn't show up a whole lot, but I'm kind of obligated to show you how that one works. This next one, though, is very useful. The other alternative is, let's say, same situation. Let's say that you have a force at that same angle theta. So the trick here is you can use geometry. The trick is that you extend the force vector. Like on your piece of paper, you draw a line, and then you drop a perpendicular from the pivot to the extended force line. Then this distance here, that distance is r sine theta. Sorry, well, yeah, it's r sine theta, which I'll leave it at that, which would be d times sine theta in this case. So then in this case, we could write the torque as the magnitude of the torque, which is just f times d perpendicular, which is that distance. This is just f times d sine theta. Now, I have to unfortunately give you some confusing terminology. I've been using this r. I've been using this thing r, and I've really been calling it r sub moment. And this value R is not the moment arm. It's like the moment, this is like the moment vector or something like that. The technical definition of the moment arm is this distance. This is the moment arm. So the moment arm is defined to be the perpendicular distance between the pivot point and the extended force line. That is how the moment arm is defined. So if you hear someone talking about a moment arm, sometimes it is just the distance between the force and the pivot point when the force is applied perpendicular. So let's do another example. If we have the pivot point here, and this distance is again d. If the force is applied perpendicular to the moment vector r, then yes, d is the moment arm. So the moment arm basically tells you the effective distance that your force is from the pivot point. It is if we applied the same force, the same magnitude of force, entirely perpendicular to our object, how far away would it have to be from the pivot point? That's what this moment arm really is talking about. So if you see that language, that's what it means. And I'm sorry that the language is confusing. It's just become convention. So by the way, notice that as the angle gets larger, the moment arm gets shorter, which kind of makes sense, right? The more or the less and less you're pointing in the direction perpendicular to the moment vector, the less of an effect your force will apply in the form of torque. So the moment arm kind of captures the amount of your force that actually contributes to the torque. Now, like, you can compute torque however you want. You could just actually do the cross product and find the magnitude. These are just a few tools that you might find useful in order to find the magnitude of the torque, which you're going to have to do a lot when it comes to statics or static equilibrium problems. Let's take another slight detour, and let's go back to talking about center of mass. I promise these will all come together soon. So let's talk about center of mass. So let's say that there are two objects, and we know where the center of mass is on each individual object. So let's say we have like lumpy object number 1, and this has a center of mass here. And then we have lumpy object number 2, and this has a center of mass, say, here. So a force at an angle and the exact force perpendicular but closer to the pivot would have the same effect based on the moment arm. Yes, that's precisely it, Rebel. So we know how to find the center of mass of a system, but what if we have two things in which we know where their center of masses are? How do we find the center of mass of the combined system where we combine this into one large system? So let's back up a little bit and write down an equation for, say, the x position, the position in the x direction, what the center of mass is for each one. So the center of mass of the first object, xcm1, is by definition 1 over the total mass times the integral over the object of x dm, right? That's just the formula for it. Whatever this means, you're just integrating over every chunk of the object. You're adding up all the little small masses of the object. And similarly, xcm2 is 1 over m2, integral over the object, let's say object 1 and object 2, x times dm, right? Again, you're just adding up the positions weighted by the small amount, weighted by the mass, and then you're taking the average effectively. You're taking the weighted average position. Well, if we were to combine these into a single system, we might want to know where the center of mass is of the whole system. So you might guess that like the center of mass might be like here or something like that. And I mean, you could be right, but it's obviously that's an estimate. And so we would need to calculate it. Fortunately, we have the tools to do this. The center of mass position is just, well, it's 1 divided by the total mass of the system times an integral over the two objects, object 1 plus object 2. And when I say plus, I mean just like integrate over both things. And then we have x times dm. But what I want you guys to keep in mind is that, remember like when you were doing calculus, if you have an integral from like 0 to 5 of stuff, that's equal to the integral of 0 to 2 of stuff plus the integral of 2 to 5, right? That's just a fact about integrals. You can basically break up the domain of the integral into separate integrals. That's allowed. So we can do the same thing here. We can break up the domain into the domain of object 1 and the domain of object 2, and then add up their results. So we get that this is equal to 1 over m1 plus m2 times the integral of object 1 over object 1 of x dm plus the integral over object 2 of x dm. But now we know how we can rewrite those integrals in terms of the old center of masses, which is what we're trying to do. So this is just the mass. This is just m1 times xc m1, right? And this is just m2 times xc m2. So what we get is that this is 1 divided by m1 plus m2 times m1 xc m1 plus m2 xc m2. Or written another way, it's just m1 xc m1 plus m2 xc m2. And there's a reason I'm going over this because we'll need it later. But the point is if you want to find the center of mass location of two objects for which you know where their center of masses are, all you do is imagine that all of the mass is at the center of mass. And then you just calculate the center of mass of the combined system together. Or the normal way, you just take the weighted position of the first, yeah, it's a plus sign, sorry. You take the weighted position of the first object plus the weighted position of the second object and divide by the total mass. This should be intuitive because all of this whole like integrating and all that business, that's taken care of by the time you already know where the center of mass is of each individual object. And then you can just imagine that they're just point masses, and then take the center of mass of those 2 point masses. And by the way, obviously this works for the y coordinate and the z coordinate as well. But the idea is you just, the center of masses themselves can almost take the place of the object. So useful fact, again, we'll need it for when we get to statics. The very last thing that we need to talk about before we get to statics, and I briefly mentioned this, I think on Monday, is that I haven't actually told you how the gravitational force acts, where the gravitational force acts. Can you just take the average of the 2 center of masses like x1? No, you can't, Christine. So imagine that that's a good question though, and thank you for asking. Imagine that the mass of this first object is like 1,000 times larger than the mass of the second object, right? Well, then you would expect the center of mass of the combined system to be very, very close to the center of mass of the first object, because almost all of the mass is over there. So you have to take a weighted average, which is why we multiply by the mass before we divide by the total mass. Excellent. Right, so the last thing to talk about is, we know, so if I just drew a diagram for you, if there was a force applied there and like a force applied there or whatever, you could compute the torque, except there is one force that I haven't told you where the force is applied, and that's gravity. Does the gravitational force apply at the bottom, or does it apply at the right side? Obviously, it's probably not the right side because that would not be symmetric. But we know that gravity acts on things with mass. So how does it act on a whole bunch of things that are glued together, a whole bunch of things with mass that are glued together? So we're just going to work a simple example here, and then I'll explain why this makes sense after we work the example. So let's consider the potential energy. Maybe we want to compute the gravitational potential energy for a falling / rotating uniform rod. So the picture here is, let's say before it falls, it's at rest like this. By the way, this is similar to what's happening in the homework, I believe. I think in homework 7, I included this is the diagram I was talking about in problem 4. So let's say that this is the before case. It's, suspended horizontally. It's just kind of sitting there. And then you let it go. Well, it's going to fall down like so. That's the length should be conserved, right? The length of the rod shouldn't change. It's going to fall down. It's going to swing downwards. So initially, let me write after over here. Initially, oh, let me back up a little bit. If we were just talking about like a ball that was at some height and then it fell down, we could directly use energy conservation. We would take y before here, y after here, and if we wanted to find the speed, say, we would use energy conservation, and we would have, delta ke plus delta pe gravitational equals 0, right? And that's all fine and dandy, except we don't really know how to compute the gravitational potential energy of an extended object yet. That's not something that I've taught you yet. So we can't just explicitly take the difference in gravitational potential energies and then use that to find the angular velocity, for example, like we would want to. So we're going to work out how that works. So assuming this rod has 0 thickness, we do know that every single one of these chunks, they all have the same gravitational potential energy initially. So the center of mass of this rod is at the height of all of them, because they're all at the same height. So they all have the same center of mass height. So the potential energy for each of those is the same. What about the potential energy for each of these chunks, though? Because they're all at different heights. So we need to figure out what is the total potential energy of the system when it's in this vertical configuration, as opposed to the horizontal configuration. By the way, the point here is that the gravitational potential energy before, well, they're all at the same height. So this is just m times g times y cm, right? Because they all have that same height. So you just take the total mass and multiply it by g and multiply it by the height, right? So that's the point here. But what about after? After, it's a little bit trickier because they're all at different heights. So let me be a little bit more explicit. So the potential energy due to gravity in the before case is, technically it's an integral because this is an extended object. We have to integrate from 0 to x equals L, say, and we integrate dm times g times y, y initial. Let me explain where this formula comes from. So the potential energy due to gravity for a small chunk of mass is just dm times g times y of that small chunk of mass, right? So if I wanted to add up and find the potential energy for the whole rod, I would have to do an integral. That's where this comes from. And that yi, that's just initial. So that's the initial height. And they all have the same initial height. So we know that this is a uniform rod. So this just works out to be g, and they all have the same height. So this is g times y cm times an integral from 0 to L of dm, but that is just by definition, it's just the total mass. So this is where we get mgycm. That's why that formula popped up. So that is the gravitational potential energy before it falls. After it falls, we have to do the same thing. We have to integrate the potential energy of each individual part, but this time, the integral is slightly less straightforward. Let's just for the sake of being explicit, let's call this line here, that is the x equals 0 line. And let's call, how do I want to do this? I want to put my coordinate system here. So we integrated from 0 to L because the position of each block was going from 0 to x equals L, and the height was at YCM. So now we need to integrate up this rod. So the integral that we do here is we integrate from 0 to L, the length of the rod. In this case, this is y equals 0 to y equals L because we're integrating upwards. And again, it's just dm times g. And this time, the position of a given chunk of mass varies with height. Or it varies with its height, of course. So this is just equal to m times g times 1 divided by m. All I'm doing is multiplying and dividing by m. You're allowed to multiply and divide by anything that you want, times the integral of from y equals 0 to y equals L of y times dm. So hopefully where this integral popped up is straightforward. All I did is I just factored out the g, and then I multiplied and divided by m. But now look at this formula here. This formula, that is the location, that is the vertical position of its center of mass. That is, let me say before, that is the center of mass after, once it is in the vertical position. So what we see then is we see that the change in potential energy, the gravitational potential energy of the system, is mg y cm after minus mg y cm before, which hopefully you've caught on now. This is just mg delta y cm. It's just the height difference that we account for when we're talking about gravitational potential energy is just the change in height of the center of mass. And perhaps from this example, perhaps you can see that gravity only cares about the location of the center of mass. One way to see this is consider, let's say you have two blocks of equal size and mass. Well, the net force on this would be the gravitational pull downwards on this plus the gravitational pull downwards on this, right? So you would add them up. And so if we're just worried about net force, the location of where that force is applied doesn't matter. But now let's say that we're talking about torque. So let's say that we have those two blocks, and they're glued together, but they have to pivot about, say, I don't know. Let's just choose the center point. Makes it easier, where the center of mass actually is. Well, we'll have a force downwards from this one and a force downwards from this one. So what is the total torque of this system? Well, it would be, this distance, or rather, the horizontal distance, because that's the moment arm, times the length of the force. So let's call this distance s over 2, side length. So the torque for this force here has magnitude s divided by 2 times the magnitude of the force. And it is clockwise, right? It would tend to rotate the object clockwise. The torque for this one, on the other hand, though, would be, well, it's still s over 2 units away times the magnitude of the force, but this would be counterclockwise. And so you'll indeed find that the net torque is 0. And in fact, even if you had chosen some other non-obvious pivot point, like maybe a point over here or a point down here or whatever, you'll always find that the net torque is 0. Sorry, yeah, well, yeah, you'll find that the net torque due to the gravitational force is 0. And that's because, I mean, that's a feature of gravity. That's because the torque always acts at the center of mass, or the gravitational force always applies or acts from the center of mass. So you could do this calculation all day, and you could figure out what where the torque is by breaking up something complicated into a whole bunch of different pieces. But instead, what we can do, and this is what we are going to do, is we just treat gravity, the gravity acting on each individual block, as an effective force that just acts at the center of mass. And that's good enough because it doesn't change, it doesn't affect the net force because the total forces will just add up. And it doesn't affect the torque either because gravity never applies a torque about the center of mass. So the whole point here is that it is sufficient to just treat. So any 2 points on an object will have a net torque of 0. No, actually, that's not quite true. Only about the center of mass or about the center line will there be a net torque of 0. But the important point is that about the center of mass, gravity will never do any torque. One way to see this, by the way, is imagine that there was no drag. Actually, let's say that you're just dropping a feather on the moon, right? Like in that video I showed you guys a while ago. If you drop a feather on the moon, the feather won't rotate at all. And the reason for that is that, well, we already know that if there were no net forces, then the object will rotate about its center of mass. That's also in the homework, by the way. Or no, that was in homework 6. If there were no net forces, the object will just rotate about its center of mass. And further, we know that if you're just, in the absence of everything else, all you have is gravity. So if gravity could exert a torque about the center of mass, then when you drop the feather on the moon, where gravity is the only force around, the feather would rotate, but it doesn't. It just falls. Now, on Earth, when you drop something, sometimes it will rotate, and that's because of aerodynamic drag, which can exert a torque about the center of mass, whereas gravity doesn't. But the important point is that because gravity doesn't exert a torque about the center of mass, the only place that you can put it so that it never exerts a torque about the center of mass, the only place that the gravity could act from is at the center of mass. So this was all just to justify where we draw our arrows on our extended force diagram. By the way, this whole business of gravity only acting from the center of mass, this is often what's called the center of gravity. That's why people will use the center of gravity and the center of mass interchangeably. But the whole point is if you have some complicated, lumpy thing, if the center of mass is here, then gravity acts from that point. That was the whole point of this exercise, just to explain why that's reasonable. So with that now in mind, we can now handle any statics problem. So let's talk about statics or static equilibrium. So I need to define these words for you. Static means unmoving, and equilibrium means not about to move. Right, so if a thing is in static equilibrium, it's just happy just to be there. It's not gonna move in 100 years, and it's not moving right now. So the consequences of those assumptions that we're making about whatever object we're studying is that the net force is 0, i.e. it's not moving translationally, and the net torque is 0 because it's not rotating. When I say move, by the way, I'm including rotational motion. So if we want to, if we are assuming some array of objects is in some sort of static equilibrium case or equilibrium configuration, that gives you a few different constraints on the forces that are present on your objects, because it tells you that the sum of all of the forces has to equal 0 and the sum of all the torques has to equal 0. Now the question is we know how to compute torque if I tell you, or you know how to compute torque if I tell you where the pivot point is, but what if there's no obvious pivot point? What do you do? Well, unlike force, torque can be evaluated in a lot of different ways. And one thing to pay attention to, by the way, it can be evaluated in a lot of different ways because the pivot point, because it depends on the pivot point, the location of the pivot point. One thing to keep in mind is that if you just have some arbitrary thing, if the torque about this point is 0, and the torque about this point is 0, and the torque about, I don't know, this point is 0, well, if the object's just not rotating, then the torque about any point is 0. So the whole point of, or one of the benefits that we get when we're studying static equilibrium is that because we're assuming it's not rotating, that means that there's no torque about any pivot point. So what we do then is we choose any convenient pivot point to calculate the torque. That's kind of, that's what makes this both easier and harder, because, you know, if I just gave you this lump and I told you it was in static equilibrium, that doesn't imply that there's any particular pivot point. It's not moving, so there is no pivot point, actually. So then which one do you choose to calculate the torque? Well, that's the point. What makes it hard is that you get to choose, but what also makes it easy is that you get to choose. And that's just because if the torque is 0 about one pivot point, then it'll be 0 about any pivot point. That's just a general feature. So it doesn't matter which pivot point you choose, they're all good. A consequence of static equilibrium is that if an object is, so any 2 points in an object will have a net, oh no, okay, that was an old question. So a consequence of static equilibrium is that you can use a system being in static equilibrium to learn more about the system. So let me give an example. So we've now defined or understood where the gravitational force acts, but what often comes together with the gravitational force is the normal force, right? And you might wonder where the normal force acts. Well, it probably acts somewhere at the point of contact, but the question is where. So we can understand by assuming static equilibrium is, assuming an object is in static equilibrium, we can understand where the normal force must act. And that's by using the fact that the net torque has to be 0 on the system. So let's say that we have, you know, on the ground, and then we have some lumpy thing, right? And let's say that its center of mass is here, so there's gravitational force pushing downwards. Now the normal force is going to be somewhere down here. Question is where? So we know that the normal force, if these are the only two forces present, we know that the normal force has to A, cancel out in magnitude the gravitational force. No, it does not act on the center of mass, actually. We know that the net force has to be 0, so we know that the magnitude of n has to equal the magnitude of mg, or has to equal mg. But that's just because the net force is 0. But we also know something about where it acts because of the torque. Now, the the normal force does have to act on the point of contact because that's where the force is coming from. It can't act on the center of mass because, well, the object is not touching the center of mass. However, the fact that the torque is 0 implies that you can pick some pivot point and compute the torque for a given position of the normal force. And then you can see if the torque is indeed 0. So the fact that, so let's just, for example, suppose that the normal force is over here. Just for kicks, right? Well, then let's choose, say, the center of gravity, or the center of mass, as our pivot point. Because we can choose any pivot point. We know the net torque has to be 0. So the torque about this, the center of mass, well, it's the, let's say the magnitude of the torque about the center of mass. Gravity doesn't contribute. We've already learned that because the moment arm is 0. And so then we would just have to figure out this distance. Let's call this distance, let's just call it L, just to give it a name. Then the magnitude of the normal force would be N times L, and it would be counterclockwise. But if those are the only two forces, then the torque isn't 0. So in fact, what we find is that the normal force, let me make this precise. If gravity is the only other force, the normal force acts so that it is in a vertical line with the center of mass. So a picture might look something like, here's our lumpy thing. Center of mass is here. So the normal force would be directly below it, and it would be applied directly upwards. And this way, regardless of where you choose your pivot point to be, if I had chosen this pivot point, I would have, say this is the pivot. The magnitude of the torque from gravity would be, that distance is, say, L again. It would be L times mg counterclockwise plus N times L clockwise. But the fact that the net force is 0 in the y direction, the fact that this is true means that N equals mg. And so we get that the net torque is Lmg counterclockwise, or let's just say clockwise is positive. So this is a minus, and that's a plus. So it's minus Lmg plus Lmg, which is just 0. The point is if the normal force is directly underneath the center of mass, and assuming there are no other forces, then the net torque about any pivot point is 0, and the net force is 0. So this tells you where the normal force has to be. Now, keep in mind that that's not the whole story, because if the net force, if there are other external forces, then or other forces besides just gravity, then the normal force will have to shift around to account for that fact. And we'll talk about this more in detail next time, but I just wanted to bring this up this time, just to give you a little taste of what you can learn from static equilibrium. All right, so I will call it there. I believe that we should be on track to get to be where I want us to be by next time. So that is excellent. All right, does anyone have any questions? Please feel free to ask. So the normal force only ever acts on one, well, yeah, okay, so let me no. Just like how gravity acts on every chunk of mass in the object, but we can treat gravity as an effective force that acts from the center of mass. Similarly, the normal force acts on every point of contact, but we can treat the normal force as an effective force acting on a single point. The reason we do this whole effective force business is because it means that we don't have to add up an infinite number of infinitesimally small forces, right? And it just makes our lives easier because all of the math checks out. But if you were actually curious, you could write all of these forces as integrals. And that's what you would have to do if you wanted to be completely explicit as the normal force acting at every point along the point of contact. But we treat it as if the normal force acted from a single point. And it's not an approximation, really. So could we say for statics that the net normal force will always be parallel to the center? No. So we're going to talk about that on Friday. But the net normal force, is not always parallel to the center of mass. In particular, what if I instead pushed down, applied a force here with some large amount of mass? Well, then you have to. You might expect that the normal force would shift to the left. And so that's indeed what happens, and we'll see that explicitly on Friday. Would you want n to always be directly below mg? No. So no. So as just explained, yeah. The idea is the normal force will move around depending on what other forces are present. Is it just given that torque equals negative length times mass and gravity? Torque is, the magnitude of torque is the magnitude of r times the magnitude of F times the sine of the angle between them. So in this case, the sine of the angle was 90 degrees. And in this case, even though the angle wasn't 90 degrees, the angle was, this thing. The distance times the sine of the angle is still L. This was that whole business of the, I can be more explicit here. If this is our pivot, for normal forces here, this is our center of mass, and our pivot is here. Well, we can do this trick where you extend the force line, and then this distance here would be R perpendicular. And the magnitude of the torque is, or R perpendicular is defined such that R perpendicular is equal to R times sine of theta, or R perpendicular being the moment arm. So the moment arm in this case was L. So that's why I can multiply L times N to get the total torque. And then similarly for gravity, the moment arm is just L because that's the distance and the sine is 90 degrees. So if I applied a large force downwards, it wouldn't necessarily start rotating, right? Let's say I applied a large force downwards here. Well, like, example, phone, hand. There's a normal force and gravitational force. But if I push down here, it's not rotating. It's still in static equilibrium. All that does is it changes what the normal force is and where the normal force acts. And again, we'll see that on Friday. Could you go back and go over the example of the change of the potential energy of the bar rotates around a pivot point again? So I actually didn't go over the kinetic energy bit. I just went over the change in potential energy bit. You have to do some of the work to find the change in potential energy. But the rotational work has a work energy theorem. So the work done rotationally is equal, or the rotational work done is equal to the change in the rotational kinetic energy. So you can combine those two facts to get an energy conservation-like thing, where you have change in potential energy plus change in kinetic energy equals 0. Why did I add the normal force time? Oh no, okay, so why did I add? So I added the normal force times the length of the torque, because the length of the force, because that is one component of the torque, right? The torque is just a force. The magnitude of torque is a force times a distance. And then there's a sine theta there to account for the fact that the force might not be in the direction of the moment vector. So that is the definition of torque. Torque is RF sine theta. I can provide you with links to them. I'm not going to write up brand new problems though, because then they'll just end up on Chegg anyway, and they might be good problems. In fact, actually, I'm going to send out an email. You guys may have heard of this this thing called, where is it? Oh, I just had it. Where'd it go? Oh, the Co-Physics 9A course. There is a Co-Physics 9A course, and it has a whole bunch of problems that you can access. They're from the paper textbook, so you will be able to see all of those because they're all available on the instructor's website for free. So I'm going to send out a link to that so that you guys can access that. I haven't yet decided how I'm going to have the exam proctored. It might be the same. I might just have 2 separate time slots for the exam to be proctored, so nobody's stuck with timing being an issue. I haven't decided yet, but I'll send out an announcement once I figure that out. Does anyone else have any more questions? Take that as a no. All right, then I will see you. Oh, I forgot to stop recording. So the recording's going to have all of that business.